Good evening, and welcome to the New England Aquarium and the Simon IMAX Theatre. This is actually the 5th annual John Carlson Lecture, and we are so delighted to partner with the Lorenz Center at MIT. We feel this is a very wonderful outreach lecture partnership. And it's really great to see so many of you here and so many of you interested in such an important and wonderful topic. And of course, water is actually our favorite topic here at the Aquarium. I am Nigella Hilgarth, and I am the president and CEO of the Aquarium. So I invite you for a minute to just think about our blue planet, about the 71% of our planet that's covered by water. And it's the only planet that we know of that supports life, though obviously statistically we know there is probably life in other parts of the universe, and we have recently discovered there is actually water on Mars, which I find enormously exciting. But water plays such an important role in every aspect of life on this planet. As you know, I mean, humans are made up of 60% water, many animals are 90% water or more, but life is dependent on water. And I think it's very important for us to understand not only how water works, but also how climate works on our planet. We read so much about enormous dramatic changes in climate recently, droughts in one area, amazing floods in another, and the devastating impacts on human lives and ecosystems. And so what does this all mean? And what does this mean for our future? What does climate change, what does global climate change mean for us? And I think it's wonderful that at the Lorenz Center at MIT, these are the sort of questions that the best scientific minds are coming together to solve some of these questions and understand the dynamics of our atmosphere and our oceans. And you're going to hear more about that from Dan and Kerry in a moment. But I just want to emphasize that I think a very important thing that the Lorenz Center and the Aquarium have in common is that we are passionate about education and about communicating climate science to the public and raising the level of public awareness and understanding of these global issues. And I want to thank the Lorenz Center very much for making tonight's lecture possible. And I'm very much looking forward to listening to Bjorn-Stevens' lecture tonight. Very exciting to hear about his work understanding climate, particularly his work on the atmosphere and clouds. And now I'd very much like to welcome Kerry Emanuel, the Cecil and Ida Green Professor of Atmospheric Science, and Dan Rothman, the Professor of Geophysics, who are actually co-founders of the Lorenz Center at MIT and co-founders of this lecture series. Thank you.
Thank you very much, and let me begin by thanking Nigella and the whole staff of the Aquarium for hosting this wonderful annual outreach lecture, and especially to thank John Carlson, who is here tonight, who is the sponsor of this lecture. This is an annual public outreach lecture. This is, as you know, the 5th one, and my colleague, Professor Dan Rothman at MIT, and I co-direct the Lorenz Center, which runs this. It's my very special pleasure this evening to introduce my friend and colleague Bjorn-Stevens. Bjorn is the director of the Max Planck Institute for Meteorology in Hamburg and a professor at the University of Hamburg. He received his doctorate degree in atmospheric sciences from Colorado State University, and after a 2-year stint as a postdoctoral fellow in the prestigious Advanced Study Program of the National Center for Atmospheric Research, went on to join the faculty of the Department of Atmospheric Sciences at UCLA. In 2008, he moved to Germany and joined the Max Planck Institute. I don't think it would be an exaggeration to claim that Bjorn-Stevens is today the world's leading authority on clouds and how they interact with the Earth's climate system. He has advanced our understanding of an amazing variety of cloud systems, from marine stratocumuli, which are responsible for much of the reflection of sunlight by our planet, to the small cumulus clouds that dot tropical skyscapes, to the tall precipitating convective systems that transport much energy and water upward from the tropical oceans into the deep atmosphere. He is, excuse me, he's also a leader in understanding how aerosol particles, including man-made aerosols, affect how clouds produce rain and snow, and how much sunlight they can reflect, both very important problems in understanding climate. Bjorn is a member of that rare breed of scientists equally at home designing and performing field experiments, working out theories, and using computers to simulate and help understand atmospheric processes. His breadth of approach reflects the breadth of his interests. He is a modern-day Renaissance man, and it is a special delight to have conversations with him on any subject at all. Unsurprisingly, he has a long list of awards and honors, too long to list for you tonight. But I have to say that he is the only scientist I know who was asked to deliver a lecture to the Bavarian State Opera. I have not yet had a chance to ask him the mode in which that particular lecture was delivered. The subject of tonight's talk is the most important and interesting component of the Earth system, water, and what more appropriate place to talk about it than here. I give you bjorn-stevens.
Thank you, Carrie, for the very flattering introduction, especially coming from someone of Carrie was always a teacher for me, so it's quite an honor to be here to present some of my ideas to you in front of Carrie, because he's been so influential to many of us in the field. So I wanted to thank you and Dan and the Lorenz Center and the New England Aquarium and John Carlson for really hosting this public event. It's really a great pleasure for me to be able to take a few minutes or tens of minutes of your time to try to talk to you about the things that I feel passionate about and see if I can communicate in the next 45 minutes some of the interesting things about water in the atmosphere. And for the people from Revere High School over here, I guess, on the right, is that right? There'll be a quiz at the end of the lecture, and we'll see how much you got. No, so to begin, the lecture is entitled Watching Water. And so you're forgiven if you wonder how I managed to get this Windows laptop on the screen for the Windows backdrop on my Mac. It's not really meant to be that. This is the image you get if you type Bliss into Google and search for images. So this comes up because the picture is called Bliss. It's from Sonoma County, and it's what Windows used for their laptop. And the thing that puzzled me about this picture when I saw it, I used to see it always on Windows machines, is why they had this picture on their laptop backdrop. And I don't know. I think they found it was a nice picture. But what is it about the picture that makes it nice? It's the sort of, I would say, you can answer that for yourself, it's the hint of water everywhere, but not in any threatening way. So you see the bounty of nature wrapped up in the rolling green fields, suggesting a fertile landscape, but a completely unthreatening sky. The dotted little cumulus clouds and the painted cirrus clouds in the background kind of offset the blue to give you this feeling of calmness and hominess. If any of you have read Lord of the Rings, you kind of could imagine if you had a big tree here, this would be the Shire. So it's the place where everyone's comfortable and at home and feels good. And so maybe that's why they used it for their laptop. And I was fascinated how much water is part of communicating the comfortness of this environment. But water isn't only about bliss. You can play the game and you can type ominous in Google and say, Google, what does ominous mean? And you get this picture. So ominous in Google this pops up if you look for a large image, and it looks like a giant jaw, a whale shark or something's about to eat what's probably some Midwestern town. I don't know where that is. But again, I found it fascinating how the sky expresses, through water, the clouds in the sky, expresses many emotions that we think of nowadays as not being connected to the sky. So the sky is really this deliverer of bliss, and it's a deliverer of threats, of ominous threats, like this one, all through water in the sky. And you can play a game. See if you can play this game. Imagine yourself thousands of years ago when we couldn't communicate in written forms, the beginning of the agricultural age, and you lived somewhere. every day was more or less the same, right? The only thing that would change, you would maybe wander from one settlement to the next, but you would live in a landscape that might slowly change with the seasons. But the only thing that really changed was the sky. And every day the sky would change. So you could imagine how people would be tuned in to the sky. If you can put yourself in that environment, the only thing that would really change is the sky. And sometimes you would have bliss, but sometimes you would have something like this. And you wouldn't know. I mean, just imagine what that's like, having absolutely no idea of what the sky is bringing you from one day to the next. And imagine how tuned in you would be to the sky and all it was delivering. So it's no wonder that when you go back and look at the stories that humanity tells and the gods that it creates, that many of the early gods were really gods that came out of the sky, because so much of your livelihood was dependent on what the sky delivered, and so much of that was told in terms of water. Does anybody know who this is? Revere? So this is aurochs, which is the predecessor of the modern cattle that went extinct about in the 17th century. And it's on the gates, the Ishtar Tor, which is one of the Ishtar gates, one of the 12 gates of Babylon. And this is recreated. If you go to Berlin, they have this recreation of one of these Babylonian gates. And this is the god Hadad. And so it's one of the very first recorded gods. And Hadad was the god of the sky and the god of rain and the god of fertility. And so it's not a wonder when you imagine how humanity developed over time that our gods came from the sky. And gods and weather and water were one and the same. So really understanding the world for people, early cosmologies, was very much connected to understanding water. So if you understood water, you understood the world. Tell that to your teachers. And here's an example, because if you go to the sort of more modern Abrahamic religions, so the Abrahamic religions that we kind of think of Judaism, Islam, Christianity, and you go to the creation stories of this tradition, creation and trying to understand the world came about by trying to explain water. And so you see it here in the left. This is a picture. I didn't use my own picture, but I saw this a couple years ago when we went to holiday in Sicily. So if you go outside of Palermo in Sicily, there's a hill that you go up, and there's a beautiful 12th century cathedral called Montreal. And in Montreal, you have these wonderful mosaics. And so this is an image of the mosaics showing the creation here on the left. And so there, the first day of the creation, where one is creating light. And the second task of the creation is written there, and God said, "Let there be a firmament in the midst of waters, and let it divide water from water." I thought this was so cool, because I study the sky, and I study water in the sky, and really what it's telling you is that the sky was created by separating water from water. And I thought what could be cooler than that? The meaning of the sky, especially I study water in the sky, and my friends study other things, and I keep telling them water is more important. And here I have proof, because to really define the sky, you had to separate water from water. And so explaining, again, the universe really amounted to explaining water in the sky. This is a painting just to show another view of this scene. So this is a Russian famous seascape painter named Ivan Ivazovsky. And a painting like this would cost you a good $1 million. And it's a seascape showing this scene of creation where water is being separated from water to create the sky. And it makes sense, doesn't it? Because imagine, again, you're back in that village 4,000 years ago or so, and you're trying to figure out why it rains. I mean, how would that happen? Of course, you'd have to separate the water from the ocean. You'd have to have a whole ocean above and an ocean below. And the rain would fall out of the ocean above. It seems like a pretty good theory, doesn't it? Try figuring out evaporation without anyone telling you it. So it seems like a nice story, and it tells you that understanding the world comes about by understanding water. The importance of water is also embedded in our folklore. And so I think a lot of you know the different folklore sayings, like the one that red sky at night. What happens? Sailors delight, right? And red sky in the morning. Yeah, sailors take warning. That phrase, red sky in the morning, sailors take warning, is found in lots of different variants. And here's a variant that I like. I'm on a Lord of the Rings theme today. So if you haven't read it, me and my daughter are reading it together for fun. And the other day I ran across this. And it's Frodo, you know, the star of Lord of the Rings, the little hobbit, grew up in the Shire. And he's about to go on this enormous adventure to save the world. And the first day when he leaves the Shire, they travel through this ominous forest and they're rescued by this singing giant Tom Bombadil. And Tom gives them shelter in their house. And so the first night they spend outside of the Shire. Shire is the Windows laptop screen, remember? That's a nice comforting place. The first night outside of the Shire, they spend, and they wake up and Frodo runs to the eastern window. And the book says, to read, it was a pale morning. In the east, behind long clouds like lines of soiled wool, stained red at the edges, lay glimmering deeps of yellow. So this is red sky in the morning. And sure enough, a little paragraph later or so, before they had finished breakfast, the clouds had broken into an unbroken roof, and a straight gray rain came softly and steadily down. So here we see this red sky in the morning, sailors' warning, because there they had a storm and Frodo had to spend a couple days at Tom Bombadil's house. And it was also pretending what was happening later in the story as he moves out of the Shire. So this red warning the first night outside of the Shire. So how do you explain something like this in folklore? And where does this come from in folklore? And it happens to come from what ends up being a fairly regular pattern in storm systems in the middle latitudes. And here you can see this with the help of a satellite image. So this is a weather satellite that's sitting about here. And what you see in the weather satellite image is clouds. I don't know if you can see, do you see my cursor up here on the left? So you can follow that around here. And what I've done is I've drawn this sweeping little spiraling red line to kind of help illustrate the pattern that you see in the cloud form. And what happens is there's giant currents of air that move around the middle latitudes from west to east in the direction of the rotation. And once in a while, they become unstable like waves, and they grow up and they curl around and wrap around. And there's a whole sequence of motion that's associated with this, is that as they curl around, cold air from the poles is pulled around behind the storm and rides up above the warm air that's associated here. And the warm air here pushes up and goes up and over the colder air that's ahead of the storm. So if you take a cross section, if you just cut this cake right from the left to the right and looked at the different clouds that would form if you're trying to understand water in the atmosphere, you might see a picture sort of like this cartoon. So on the left side of the storm, you would see this cold air coming from the north, cutting under the warm air. And because you have this would be what you would call the cold front, and often you'll see intense convection associated with the system here. And then you see the warm air that's rising up through here, and it's pushing up layered clouds up along a slanting until you have high cirrus clouds up in the atmosphere. So it's pushing moisture up into the atmosphere. So storms have this structure. And ahead of them, you know, every storm's a bit different, but there's patterns in the storms, and this is a common pattern. Here you would have fairer weather, cloud-free fairer weather, and here I just drew it that in the fairer weather you might have a dust-laden atmosphere because it's fairly dry. And so what happens if you have a storm system like this in your Frodo, in Tom Bombadil's house? You're looking out the eastern window. So of course you're on the Earth is curved, and so that's how we get a sunrise. So here's the same thing, I just curved the image. And you imagine here's Tom's house. Frodo's looking out the eastern window. The Earth is rotating into the view of the sun. We call it sunrise. And what happens is the sun's light is going, the sun's down here on the bottom right, and it's going across the horizon. A sunbeam would kind of go up this way. But as the sun travels through this relatively dry and dusty air, the blue light is scattered away. So the dust particles are very efficient at scattering the blue light away. And what's left behind is only the red light. And the red light goes up here and hits the moisture in the upper atmosphere. And if you're down here and you look up into the eastern sky, what you see is all of these clouds which have been pushed up there are turning red. So it's a hint. It's a hint that maybe something's happening. Of course, you could get this for other reasons, and not every storm would look like this, and sometimes you would see that. But if you have nothing else, you know, if you're Frodo and all you have is the window to look out and your life depends on it, then you might decide you don't want to start out on a precarious adventure on the day that the sky's red in the morning. But you can also see what great advantage you would have if you didn't have to just look out your window if you could call somebody up who happened to live over here, or better yet here, and ask what happened out their window, or if you could call someone up who lived here or here or here or here, you could get a much better picture of what was happening in the atmosphere, and you could use this picture to sort of project forward in time to what was happening with your weather. And about the mid-19th century, the telegraph was discovered. Can you imagine what a revolution that must have been? I mean, the idea that you could now know at remote places of the planet what was happening exactly now, that you could transfer information across space in an instant. I mean, we take it all for granted, but just try to imagine for a second how that was, that the only way to get information from one place to another was to ride your pony, if you had one. That now you could communicate that instantaneously. I mean, a change in humanity I don't think could be anywhere as profound as that. And here you see how popular it was, because when the telegraph came up, telegraph wires were everywhere. I mean, this is the first internet, if you like, right? So you see the internet everywhere. And just think of the advantage this had for understanding weather. You didn't have to look out your window. You could begin to reconstruct how weather systems existed spatially and try to project them forward in time. Maybe you didn't quite know how everything worked, but you knew the structures, and from the patterns you could imagine how things would evolve in time. And I like these pictures. When I got this one off the web, it said something about this being at one of Boston's train stations in this blizzard of 1888. And it's a famous blizzard because what happened was a lot of the power lines, this is New York, fell down. And so I like it because the telegraph became very useful for predicting the weather. These are some of the very first weather forecasts from Admiral Fitzroy, who was the captain of the Beagle and was famous for developing the first weather forecasts, which were published in the Times of London in around 1860. And so the telegraph was very good at helping people predict the weather. And the weather got it back here, so this is the weather's revenge on the telegraph. And so after that, they decided to bury the telegraph lines. So now imagine if you have the telegraph and you want to say how the weather systems are evolving. So what would you do? I mean, what could you observe? So you have someone, you have someone all along the train line or all along the telegraph line, and they're observing. But what would they observe? They could take a barometer, and they could measure the pressure. Okay, so they could tell you the surface pressure. They could tell an anemometer, sort of a fan, and they could measure the wind, so you know the wind. You could measure the temperature. You could take horse's hair or something like that and measure the humidity. So that's what you had. You had a sort of flatlander's view of the atmosphere at this time. You could communicate the information, but the information you had to communicate was very limited. So imagine you're trying to figure out how the atmosphere is evolving, but you just get this flatlander view of what's happening at a point, at a spot, at the ground. So it'd be nice if you could do better than that. And so what did people do? If you wanted to know what was happening up in the atmosphere itself, what could you do? You could look at the clouds. And so the very first cloud atlas came out in 1890. And it was a cooperative work. One of the real drivers of this was this guy named Vladimir Köppen, who was a really remarkable person, actually, and one of, I'd say, the unheralded fathers of Earth system science. And he worked as a sort of itinerant professor at the German Seeweteramt, the sort of sea weather office, under the guidance of this other guy named Neumayer. The German Antarctica Research Station is named for Neumayer now. And the other guy, if I go back, sorry, the other guy up here is Hugo Hildebrand Hildebrandsson, which was a Swedish professor. And they realized that to explain what the current weather situation is, it would be very useful to observe the clouds. Because by observing the different types of clouds, you could understand what type of weather systems you had. And by observing how the clouds moved, you could get information about how the winds in the atmosphere at different levels were changing. And so the idea was, if you want to observe the clouds, we all should be thinking about the same clouds. And so they developed this program to have an atlas which described and built on early cloud classification schemes from Luke Howard. Many of you might know this Luke Howard classification scheme of clouds, where you have names like stratus and things like this. The name cumulus was actually an invention of Hildebrandsson, the first author here. And that's why I took from this atlas the plate 8, which shows the cumulus clouds. And I really like this picture for a couple reasons. One is, when you look at it, it makes a reference to the folklore. Because what do you see in this image? You see a shepherd here with his dog. And what's the shepherd shepherding? Anyone know? Sheep, but where are the sheep? In the sky. So the shepherd is shepherding sheep clouds. And the German word for a cumulus cloud is Schäfchenwolken, which means sheep cloud. So little sheep clouds. And the saying here from the folklore is, wenn Schäfchenwolken am Himmel stehen, kann man ohne Schirm spazieren gehen. So that means when sheep clouds are sitting in the sky, you don't need your umbrella nearby. So you can go for a walk. And so it's again this Shire-ish view of fair weather, these little sheep clouds, cumulus clouds. And they wanted to use images which were painting. You could photograph at the time. They take photographs, but the photographs weren't very well delineated. And no photograph was really perfect because the clouds are always so changing in form and between different forms. You never really get a perfect photograph. It's much better to draw it. It's much more of a platonic cloud, the cloud that you imagine in your head. And you could control this by drawing clouds. And so by systemizing the cloud types, you could then have observers all around the telegraphic network, observing the clouds, how they move in the sky, and learning something about the weather. It turns out what's fascinating is that in the very early days of weather forecasts, we did the weather forecast by watching the clouds in the sky and how they moved. And what goes around comes around. Things aren't so different anymore. So if you go back to this image I took from the Meteosat, it turns out that they have a team there working at this European Meteorological Satellite Organization in Darmstadt, Germany. And what they try to do is develop algorithms for doing exactly what they did 100 years ago, following the clouds in the sky. Except they use the satellite. So they use the satellite image, and based on the satellite, you can measure how high the clouds are in the sky. And from one image to the next, you can track how they move. So the clouds in the sky as seen from satellites are a very good way of tracking the winds. And here's a reconstruction of the winds, and they're colored. So the light colors means you're high in the atmosphere, maybe 8 kilometers high in the atmosphere, 5 miles up here. And this might be about a mile up in the atmosphere. So these are clouds which are fairly high here, and they're moving this way. So using the clouds, you can reconstruct the motion in the atmosphere. And it turns out this is quite important for modern day weather forecasts. Today, it's been an amazing progress in numerical weather prediction. We can make a weather forecast 7 days ahead of time, which is as skillful as it was 2 days ahead of time or 3 days ahead of time when I was a child. And a big part of that skill comes from our ability to observe the sky. And what I show here, this is the 7-day forecast, so you can check me out here. I did it yesterday or this morning early, I forget when I got this, but Thursday it's supposed to be 68 and partly cloudy. So in a week you can call me up if it's messed up and say it wasn't very good. And you ask what makes the forecast good? And so scientists do experiments where they sort of withhold information from the forecast models and ask how important is that information? And you can say about 10 to 15% of the skill comes from watching clouds, watching water in the sky. But about another 50% comes from these funny satellites, AMSU we call that, the Advanced Microwave Sounding Unit, if I remember that acronym right. What do you think this measures? What's the lecture? Water, right? So it measures water in the sky too. It tends to measure water vapor. And it turns out that water vapor is something that emits radiation in the infrared, in the thermal infrared, in a way we'll see in a second, in a way that allows it to be detected by satellite very efficiently. And so watching water vapor, and these are very high spectral resolution instruments. They also, more often than not, are focusing on the emission of radiation by water. So watching the sky is mostly about watching water. So now I want to transition a little bit. In the beginning, I was saying water helps visualize and predict weather. And so watching water was very important for understanding what was happening in the world and explaining the world. And it's important today for understanding and predicting weather. But do you ever wonder why we have weather? I mean, it's good for the most part, unless it's last winter here in Boston, which I guess got a bit old. But having weather is a lot of times people say it's because of the standard explanation is that the Earth gets more heat at the equator and less heat at the poles, so you have these big temperature contrasts which drive weather. And that's one reason. But an underappreciated reason is because of water in the atmosphere. So water does something very strange to the atmosphere that makes it rain. You kind of think it rains because there's water in the atmosphere and the rain falls down, and that's true. But the whole hydrological cycle, the whole process of generating weather systems is driven by a special property of water, and that's how it interacts with radiation. So I'm going to give you a little exercise in radiation, and this is what the quiz will be on later at the lecture. So I just wanted to say here, water makes weather and helps determine the climate, because the climate is sort of the envelope, the pattern of the weather. But to understand this, you need to understand something about radiation. So radiation, it's a pretty weird idea. Radiation is how bodies exchange energy, even through a vacuum. And we can see some radiation, electromagnetic radiation, a very small part of the spectrum with our eyes. They evolved in a way that's very sensitive to wavelengths of radiation or energy of levels of radiation, which are transmitted by the sun efficiently. So we can use the sun's energy to see our way around. But there's lots of other variants of radiation which have longer wavelengths, which we can't see. And it turns like at Earth-like temperatures, rather than sun-like temperatures, radiation is emitted all around us. You don't really know it, but if you feel cold or warm in a room, it's the radiation that's coming from the walls. So this wall, if these walls were at very cold temperatures, we would feel cold because we would not feel the radiation coming from the wall to heating us. We'd be losing radiation. And so what I want to do is I want to do a little experiment. Let's see if this works. So this here is a camera. And it's this camera right here. You see that? And the thing about that camera is it measures, it's a night vision camera. So it measures infrared radiation. It doesn't measure visible radiation. This is a polar bear. And so this is a cold polar bear. And this is a warm polar bear here. And so if you put them in the camera, let's see what happens. So, well, there you saw me. You see this guy's very dark. And then the other polar bear, that's my hand that's in the red, and the purple is the polar bear. And then this other polar bear is going to come by, and he's like, "Ah, I'm a hot polar bear." Okay, so this is a global warming polar bear, and this is an ice age polar bear. They're both relatively happy at the moment. But the point is you get this, that this camera sees radiation that's at a wavelength that our eyes can't see. So our skin is a pretty good detector of infrared radiation. It feels heat being radiated. But it's conceptually hard because you often think when you feel heat from a fire or a stove that that's sort of the air currents coming. But really the radiation that travels, even if there were no air, is what's being transmitted here between the hot bear and the cold bear. So now we're going to get further. This is getting complicated. So the bears are going to go to sleep here. They're hibernating. And we're going to make a solar system. So we have to take a sun, because what's a solar system without a sun? So here's our sun there. And okay, let's see, the sun's there. But what's missing, the camera's a bit slow. I don't know if you noticed that. It has a jerk, but that's because the infrared cameras that are portable aren't a very new thing. Anybody know what this is? Can you see what this is? It's Earth. Okay, so we're going to put Earth in the sun. There he is. Look at that. Earth is heating up. That's how it works. I mean, the sun heats up Earth. Let's move the camera a little bit. Yeah. So the sun shines on Earth and heats it up. And it keeps heating up until what happens? It loses its energy, so it keeps warming up, and eventually it radiates its own energy away at Earth-like temperatures. And that's what we're seeing. We're seeing that the Earth is warm, and it's giving off energy, and that's why it shows up brighter in the infrared camera. Compare him to the cold polar bear here. Right, so the polar bear is on the North Pole up here. Right, so the polar bear was purple and cold, and that's because the Earth is warmer and it's giving off more of this radiant energy. So if the Earth didn't have an atmosphere, that's how it would work. It would get sunlight, it would warm up, and it would keep warming until it lost as much energy it was getting. But there's something about the Earth that makes it interesting, is that it has an atmosphere. And you know what's in the atmosphere? Water. So we need an atmosphere. This is the atmosphere. I couldn't connect the atmosphere to the Earth, so we're just going to pretend this is the atmosphere. There's two Ziploc bags here, kind of held together. And sure enough, you still see, let's get this out of the way. You still see the Earth more or less, the red ball. People see that? The red thing on the right, that's the Earth. And the camera can see through the Ziploc bags. It's transparent. And the light also goes through the Ziploc bags. So the energy goes straight through the atmosphere and heats the surface. Everything's the same. But what happens if, now here's a chance to make a real mess. The atmosphere has water. So we'll try that, and we'll see what happens. So I'm going to pour water in the atmosphere, and here I'm using liquid water. It could be water vapor, but then I'd have to have a deeper atmosphere. Uh-oh, what's happening? The Earth is disappearing. Stop it! Oh! Oh, it's gone. It's invisible. So what happened? The water is not transparent to infrared radiation. So the water in the atmosphere is inhibiting the transfer of heat from the Earth to space. It doesn't get to the camera. This is outer space. This is the atmosphere. And normally the radiation from the Earth, which was warm, would get to outer space to the camera, but it doesn't get there because the water's in the way. And the water absorbs that energy. And this leads to a very different balance of how the atmosphere works. And this is why we have weather. And I'm going to try to explain that in a few slides. But the important point is that because of water, we can kind of look up a little bit. Look up, come back, Earth. There you are. And there he goes away again. Because of this opacity of water in the infrared, you have a very different process in Earth, and this is very important for understanding both weather and climate. So let's go back to the presentation. And this was the black slide. Before we do that, what I want to do is now go to space and look at the same thing, and then we'll go and explain that in a little diagrammatic method. So what I'm going to show you now is, instead of this infrared camera looking at Earth on the camera, I'm going to go to a real infrared camera that's on a satellite, and it's looking at water vapor. And I want to give you a sense of what Earth looks like if you look down at Earth with infrared eyes. And it's a very different planet. So there it is. I don't know if most of you would have guessed right away that was Earth. Maybe you would have. But this is what Earth looks like with infrared glasses, looking at the wavelength where Earth gives up energy as measured by satellite. And you can let it go in motion. And so here the clock talks about a day, and what you see is how water swirls around. And really, it makes our planet look like a giant gaseous planet, because if you look in these wavelengths of thermal radiation, all you see is water. And you're seeing the water give off energy into space. So the atmosphere is cooling continuously as the water in the atmosphere radiates its energy out to outer space, and that's what's being measured here. And you can see areas where there's very little water, like here, and areas where there's lots of water, where it's very white. And here what we've done is we've now gradually made the water a bit more transparent, so you can see what's underneath. And now you can see some familiar things, like the continent of Africa. And here, the edge of South America. These are the tropical zones where you have a rich amount of water vapor and deep convective storms. And these are the wonderful subtropics and the trades here and here. So very dry areas where you can see all the way to the surface because there's so little water. And very areas, even though we've made it fairly transparent, where you still hardly can see the surface because there's so much water. And so water is this very driving force in our climate system. You can see the daily cycle. Watch here. This will be Africa. The bright clouds are going away. And around noon, boom, the convection, the clouds go up, and there they go. And then a little bit later, boom, there they go up in South America. We'll go to the next day, and here they go. Boom, there they go again. It's like clockwork. And then here, boom, there they go again on the left. So you could look at these images for a long, long time. But I wanted to give the view of how water is such a fundamental component of the atmosphere, and so much of what we know about the atmosphere is connected to the water. And now I'm going to do the ABCs of atmospheric circulation. And really understanding something about water's role in the climate system, I say, is as easy as ABC. I'm going to move the sun away. So A is that visible radiation, the sun, shines down on the Earth and heats the surface. Not so hard. We know what that feels like. You can, here, this is, you could forget about these graphs, but they're really just showing distribution with height here of both humidity, the amount of water. There's very little in the high atmosphere where it's cold, and there's a lot near the surface where it's warm. And this would be temperature, which cools with height until the top of the weather layer. So it turns out the water in this weather layer here, before this minimum, is what ends up being important. And the sunlight comes down and it cools the surface. It gets absorbed by the dark ocean. It makes it warm. And the atmosphere, because of the water in it, radiates energy away. So you have this system where the surface is heating and the atmosphere is cooling, right? That's the basic thing. The atmosphere, because of water in it, is losing energy because water likes to give away thermal energy. It's very generous with thermal energy. It likes to absorb it and likes to give it away. And so the atmosphere is cooling and the surface is warming. So something has to give, right? Otherwise the atmosphere would get really cold and the surface would get really warm. And so the way that gets balanced is convective clouds develop to evaporate water from the surface. Evaporation cools, that cools the surface, combats the warming, that's C. And the water that's evaporated in the surface condenses in the atmosphere and forms rain. And that satisfies this heat balance. So the basic way in the atmospheric works, this basic heat balance, is that the atmosphere is cooling and the surface is warming. And convection arises, convective clouds that form rain, to resolve that tension. So the funny thing is that the atmosphere produces rain because of water, but not because that water forms rain, but it's because of the water giving up this thermal energy. So kaboom, convective clouds like this rain, but they rain, I hope you can imagine in the back of your head a little bit, they rain for an entirely different reason than you might have thought before the lecture. They rain because they have to rain to satisfy the heat budget of the atmosphere. It's the only way, or it's the way the Earth works to get the heat that's poured into the surface by the sun to balance all the energy that's lost by the atmosphere to space. Do you know another name for an atmosphere that works that way? There's a special name for an atmosphere that works where the atmosphere sort of shields the surface from the heat loss by absorbing the radiation from the surface, makes the planet invisible in a way. And the atmosphere cools by losing radiation to space. Does anybody know what that's called? It's the greenhouse effect. This is the greenhouse effect that you saw. So you get to see the greenhouse effect on a desktop. That's one reason why scientists don't find it such a complicated thing to talk about. If you can make it in a lecture hall in a desktop, it can't be anything too mystical. And clouds rain because of the greenhouse effect. So we like the greenhouse effect. It's what makes the planet habitable. But it's also so I said here, hopefully you get a whole new perspective on the greenhouse effect. But it also, I hope, communicates to you that understanding the greenhouse effect also means understanding water. And there's two aspects to this. So when you think about climate and climate change, like water, I could have done this with CO2, and you would have seen a similar effect. So CO2 is also a greenhouse gas, and water is a greenhouse gas. And what happens when you put more CO2 in the atmosphere is the greenhouse effect from the CO2 makes it harder for the planet to lose its energy to space, and that makes it warm up. And as it warms up, the atmosphere contains more water. And water is the most potent greenhouse gas there is. And the extra water in the atmosphere makes the Earth warm up even more. So if you want to think about what's happening in terms of climate, you could pay attention to the temperature, you could pay attention to the CO2, but you might just want to pay attention to the water. And here's an example of satellites measuring water through the atmosphere. And this shows that since 1990 to 2010, you don't have to worry about the unit, but there's ups and downs. This is what happens when you have an El Nino. The atmosphere warms a lot and the amount of water increases. But there's a steady increase in the total amount of water that's in the atmosphere. Our little window here is being filled up more and more. And this is what is most effective in trapping the heat in the atmosphere. So this is a little bit of an example of the greenhouse effect. Water, it turns out, in the atmosphere doesn't kind of go there on its own. It's very much connected to the temperature of the atmosphere. So when you do something like make the sun hotter or colder, the atmosphere will be warmer or colder, and you'll have more or less water, which would amplify the effect of the sun varying. Or if you add greenhouse gases like CO2, which is long-lived, it makes the atmosphere warmer. It's a very interesting ballet going on because you can think of, the water in the atmosphere is important for making it warm, but it depends on what the temperature is. And so sometimes you can think about CO2 and water as being in this wonderful pas de deux, this dance of two. And so here you have this dance of two, and I like to think of CO2 as the greenhouse gas. It's very long-lived. When you put it in the atmosphere, it stays there forever, and it makes the surface warmer, which then brings more water. And so if you watch this dance of two between CO2 and water, you could pay attention to CO2, the guy with the big muscular legs on the right. But I think if there's anything more interesting to watch, it's probably the water molecule on the left who's being led through the dance between CO2 and water. So if you think about the greenhouse effect, you can think about it like this dance of two between water and CO2. But watching the water might be more informative than watching the CO2. The last point I want to make is that I talked here about water vapor in this dance between CO2 and water, and that's very important for the greenhouse gas effect. But there's something else that goes on when we think about water. And we're back to our cloud atlas, because when we look at a picture of the Earth, what we realize fairly rapidly is that big parts of it are white where the clouds are. And so our sun, whoops, I don't want to blind anyone, but our sun here, I wonder if this works. Let's see. Does this see if I can get carried wet. Do you see that? Can you see that in the back? So the light is scattering into these little drops. These are clouds. Clouds scatter light. That's why you see it. So little drops of water are clouds. And clouds scatter light, which means that for the most part, clouds work in opposition to water vapor. They actually work to cool the planet. So one of the big questions when we think about climate change and how much the planet will warm as we increase CO2 and water vapor is, will it be cloudier or not? If it's cloudier, then maybe it won't warm so much as we thought. If it's less cloudy, it might warm more than we thought. And so while we're pretty darn sure that the Earth was going to warm by increasing amounts of CO2, we don't know exactly how much and how rapidly. And the reason we don't know is because we don't really know what's going to happen to the clouds. So in a way, we're back to where we were 100 years ago of charting the atlas of clouds to try to figure out what's happening to the climate. And I'm going to show you just 2 slides about some research we're doing at my institute. And the first slide here shows you why we're interested in the clouds. So this is a view from the Pacific Ocean, and it explains why we think of Earth as the water planet. Not the ocean planet, the water planet, because look at all the fresh water that's buried up here in the clouds. And if you look at broad swaths of the subtropical ocean where it's a little bit less cloudy, there's lots of little clouds here. And the real question in climate change has been, how will those clouds change? And so we construct these fairly elaborate models of the climate system, which use lots of electricity to compute what's happening with the climate. And depending on what assumption you make in a model like this, you can get a solution which says, if you look at the clouds in this region here, and you look at height here, this is going up, this is about 4 kilometers in the atmosphere, and this is the amount of cloudiness. And this model says that as you go up in the atmosphere, you'll go up about 500 meters or so, and then suddenly the amount of cloudiness will increase a lot. So a quarter of the sky will be filled with clouds. And then they won't be very thick clouds. The clouds will be about 500 meters, they go away, and above them it's fairly clear. Fine, you can imagine scenes. It looks like that little picture of the sheep cloud day. It turns out if you have a model like this with lots of low clouds over the ocean, and this is our example, and you make that model warmer, what happens is a lot of these clouds go away when it gets warmer. And if those clouds go away, that means the planet gets warmer more rapidly. It's sort of a positive feedback. As you're warming the planet, the clouds go away and it gets warmer. And so this model, it turns out, makes it seem like the Earth is going to warm a tremendous amount from an increase in CO2. Now you can play a little game in the model and you can change how the clouds mix with the atmosphere, and you can get a profile of cloudiness that looks more like this. So it's more distributed in the vertical. The clouds don't have as much cloudiness right at the base. They're only, say, 10%. And the clouds go somewhat deeper. And it turns out in this model, which has slightly different rules, that as you warm it, this is the change in the clouds don't change hardly at all. And so it turns out that the light green model is about half as sensitive to CO2 as the dark green model. And one of the big questions in climate change is how fast will it warm and how much will it warm? And the difference amounts to the difference between these 2 different models of the atmosphere. And the question that's fairly simple is which one, if either of those 2 are right? And so to answer that question, we've taken a bunch of instrumentation from the lab we have in Hamburg, Germany. And we decided to go to some place where those clouds are found in great variety, Barbados. So we used Barbados as a sort of ship in the subtropical ocean to try to figure out what's happening to the clouds over the ocean over time and how they respond to changes in their environment. And so we're looking at cloud scenes that look like this. Our laboratory's here. You'll see it when the sun rises. The sun is rising over here. And we're really trying to figure out how many clouds are down here at low levels versus how many clouds, if I just pause that for a second, we really want to see what is the vertical distribution of clouds. And you'll get a flavor as we go through the time lapse of the day how challenging this is. Because you'll see, just even looking at this picture, and you try to figure out how many clouds are down here at about 800 meters. So the base of this cloud is maybe 700 meters, and this might go up to 2.5 kilometers. And really what we're trying to do with an advanced set of instruments here is more or less just count clouds, like the shepherd by the rock. And so if we let it move forward, you can see how the clouds evolve. And so you see the sun will rise here, and the clouds will start moving. And there they go. There goes the sunrise. And you see all the clouds going up, and they go up, and they mix with the environment, and they go up. And here up aloft, you see it's fairly dry, a blue sky. And then here in the back, you might see there's a hint of deeper clouds and a bit of rain. So some of the clouds will get really deep, and they'll rain. And sure enough, boom, here comes the rain. There, and here's another deeper cloud with lots of rain. And as it started raining, what you find is there's a lot more moisture in the upper part of the sky. That's up here, this layer up here on the top left. So there's a lot more moisture because those raining clouds got very deep and they injected moisture high into the sky. But mostly we're interested in how these clouds behave down here and how they change. Here it's still lots of rain off to the south. The sky's still fairly cloudy aloft, another rain shower. Now we stop. Look here on the right. Look at these clouds. The rain's moving off to the south. These are the darker clouds. But that one goes up, and you see the moisture is shot off, and then it's going up into the upper layer. So the clouds that form up in the upper layer are from raining clouds that form near the surface. And you can look, now it's much drier in the upper atmosphere. There's a hint of moisture here coming in from the south. But here's a big cloud. And you say, this guy's going to rain, right? So this is one of the things we want to know on clouds. This one's going to rain. It's getting bigger. It's bigger. The rain's coming. It's coming. It's coming. It's coming. It's coming. Whoops. Right before the punchline. Hold on, we'll get to that. We can't. I got too excited by the button. You see how exciting cloud scientists get. Then one more. We won't go through the whole movie. I'll fast forward. And then let's go down to here. This is the cloud that went off to the left, so you can watch this guy again. Boom. And then we're going to go in this deep cloud, and is it going to rain? See, it's coming. Well, it's in the back here. And it's a very dry sky now. So it's dry because there's not many clouds above. But this guy's persisting. He's getting up. And in slow motion, we're going to see, here's our station over here. Is it going to rain? Is it going to rain? It's going big, 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 big. Boom. And then it just disappears. It just goes into a whole bunch of fragments. So these are the things we're trying to figure out, is what controls the pattern. It's a pretty good job, isn't it? People pay me to go to Barbados and sit up there and look at the sky. And we put all sorts of toys here, and we watch the sky go by, and we've been doing it for 5 years. And the hope is at the end we'll have a good idea of whether cloudiness is likely to increase with warming or decrease with warming. And because of that, then we'll have a much better idea of how much trouble is in store for us if we don't do something about the tremendous amounts of CO2 we're putting in the atmosphere. So with that, I'll thank you for your time.
So after that stunning way of ending such a fascinating lecture, we have some time for questions. And as you consider asking a question, I'd like to specifically ask some of the students in the audience, especially those who haven't gone to college yet, high school, middle school, and so on, if they have any questions, and let them take priority at the moment. First, I see somebody who's probably not in elementary school in the back. Any of the students? I see some students here. You know who you are. You can still ask some questions later, so think about it. There's a question in the back. So the question, which you can't all hear, but we can, is to comment on the role of methane in the atmosphere.
Okay, so methane is a greenhouse gas. And greenhouse gases are ones which are very effective at emitting and absorbing radiation in the infrared, in the thermal infrared. And they have this property, a water molecule looks like that ballet dancer because there's the big oxygen molecule and two little hydrogens off it. Methane has a carbon and four hydrogen molecules. And so you can imagine if my body is a carbon molecule and my legs and arms were hydrogen molecules, methane sort of vibrates in ways that makes it very vociferous in absorbing and emitting infrared radiation. And because it's a greenhouse gas, the more methane in the atmosphere, it has a similar effect of CO2. The thing that's different about methane from CO2 is that CO2 is very stable. So methane will put in the atmosphere and it won't stay there forever. It will stay there. I think the lifetime of methane, someone who's more of an expert on that could correct me, is something like 7 years or something like that. And it oxidizes into carbon dioxide. While it's there as methane, it's actually a more potent greenhouse gas, as far as I recall, than CO2 itself. So it's quite an important contributor to the greenhouse effect of the atmosphere. And through a variety of activities of humans, you have a lot more methane in the atmosphere, but also through a variety of natural processes, methane is released in different ways, you know. And so there's big questions in the atmospheric science as the Earth warms. Will there be a lot more methane released into the atmosphere, particularly when things oxidize? So if you have dead stuff, normally dead stuff, when it oxidizes, you know, tree leaves, when they rot, they give off CO2. But if you do this in an anoxic environment, then you release methane. So in high permafrost regions where you'll have a lot of low-lying water, they'll give off a lot of methane. And so as the permafrost regions melt, there's a lot of concern that a lot of carbon will come out of the frozen ground, first in the form of methane, which has a big effect, and that will oxidize as CO2. So it's a long answer, and the short answer is yes, it's an important greenhouse gas, and it's important to understand what's happening to methane to understand potential sources of climate change.
Question here.
Question. Carbon dioxide in the atmosphere is in parts per million.
Yeah.
Water vapor's got to be a lot higher than that. You assert that water vapor is a bigger contributor to trapping heat than carbon dioxide. How's all that fit into the climate models that are being developed?
Yeah.
So the question is about the relative contribution of water vapor and carbon dioxide to
the thing that makes water vapor and carbon dioxide so different is that water vapor has this thermostat with it, because as air cools, then the water condenses and falls out. And that's why when you go to a picture like this, which is a typical profile here, as you go up in the atmosphere, you have less pressure and the air expands and cools. And that's why the water decreases exponentially. It decreases tremendously as you go up with height. And so the amount of water in the atmosphere is very much controlled by its temperature. And so if you had no other greenhouse gases, long-lived greenhouse gases, it wouldn't, so if you got rid of carbon dioxide, even though water vapor, it's a funny puzzle, but it's sometimes hard to visualize. Even though water vapor is a far more important greenhouse gas, it doesn't get there by itself. It sort of has to be bootstrapped by the other greenhouse gases. And CO2, because it's so stable, it gets in the atmosphere and it stays there for a long, long, long time. And that warms up the surface, and that warms up the atmosphere, and that gets more water vapor. So I always see water vapor as a bit of an accelerator for CO2, and that's why I had this picture of the dance. So water is a much more effective greenhouse gas, but it doesn't get there by itself. It needs to be drawn into the dance, so to speak, by a long-lived greenhouse gas like CO2. So I don't know if that answered your question, but that's how I...
So we'll take that question in a moment, but I'd like to suggest that the questioner stand up, and that will help the voice project a little bit. So if you don't mind standing before you ask the question. Thank you.
Yeah. I was wondering if melting ice caps and rising sea levels have any kind of measurable effects on clouds or climate change?
The question is about melting ice caps and rising sea levels on clouds.
Yeah, so the melting ice caps, especially when you look at there's two types. There's the great ice sheets, which are on land, and then there's sea ice, which is floating on the sea. And what happens in the winter, as you go into polar night at the North Pole, polar bear comes out. So as you go into polar night, you have a lot of loss. You're not heating up the pole anymore, and the oceans are fairly warm, and they're giving off tremendous amounts of heat. And when they do that, they lose heat at the surface and they freeze. Okay, no big surprise. So they freeze, but as you melt the ice, and that insulates the ocean in a way. The ice stops the heat transfer from the ocean to the atmosphere. And so the ice caps work as a bit of an insulator, a lid on the poles. And when the ice caps recede, you're able to transfer more heat from the surface and evaporate more. So there's this interplay between the ice caps and cloudiness that frankly we don't understand very well. So the one question is, if you think of the ice caps, they reflect sunlight. But if they're covered with clouds, then it doesn't matter, right? So the ice caps might get smaller, and you would say, oh, we're reflecting less sunlight. But because they get smaller, you're getting a lot more evaporation from the ocean that's sort of freed behind them. You get a lot of clouds that sort of compensates for the fact that you have less ice from the point of view of the amount of reflected sunlight. So this is a big open question right now, is how the clouds interact with retreating sea ice. Sea level, I don't see an obvious connection between how sea level behaves and cloudiness, although there are relationships between how cloudiness drives circulation and what that does to sea level. But sea level itself, I don't see a strong effect on cloudiness. There were some questions over here. Okay. Oh.
Let's go back down first. Yeah.
So I'm wondering what's your take on the upcoming United Nations climate change negotiation is, and how their overall goal is to create an agreement between nations to reduce the amount of greenhouse gases in the atmosphere and keep our temperature rising over 2 degrees Celsius.
Right.
So the question is about possible agreements to limit increasing greenhouse gases.
So the question was, what's my take on that? And I think my take is that if governments and societies can use scientific information to be conservative and protect us against risks to our environment, which global warming certainly is, that's a good thing. And so I hope that collectively, that we can take what I think is a sort of a prudent course and try to insulate ourselves against risk. And it's something that it seems much easier to do if we do it collectively, in terms of reducing CO2 and CO2 amounts. I must say, I kind of like polar bears and water and stuff like that. So I don't really follow the politics, even though maybe as a climate scientist I should. And I have sort of views on that, but I don't know all the issues of the politics. And I can talk about the science, but I'm not so good at talking about the politics. So you can ask me, but I might not be of so much help, sorry.
There was a question here.
Yes. Looking back to the short movie they had showed us with all the clouds over Barbados.
Yeah.
And while you said that when we saw one of the clouds dissipating, almost like randomly, do you already have some theories as to why that occurs in terms of water and other greenhouse gases that are in the atmosphere?
The question is, if Bjorn understands why clouds can dissipate so rapidly.
Yeah, so I have a former PhD student who's sitting in the audience right here in the middle of Louisa Nyans, and she's supposed to be figuring all of that stuff out. But so we could ask her. But it is a real question about, this is at the heart of cloud science in a way, is trying to understand what controls the vertical distribution of cloudiness. And here certainly what we saw is at the end of the movie, the tracer of how dry the sky is above is how blue. So if you see like here, the sky above is fairly dry. There's very high clouds up there from convection far away. But the atmosphere is fairly blue and you don't see very much rain and the clouds don't get as deep. And then later on, when you see these big patches of raining clouds that will develop, then you'll see a lot more of this sort of mid-level stratiform cloud going across. And so the clouds are forming in a more humid environment. And so then they don't break up as much, and it's easier to form rain because when they mix with their environment, they don't evaporate as much. Late in the movie, that cloud is getting unusually large, but it seems to be in a very clear and dry environment. So this interplay between the cloudiness and its environment, how dry it is, certainly will determine how deep it gets and how likely it is to form rain. But on the other hand, the cloud makes the environment moist. And so there's this interplay between the environment and the cloud, and that ends up being a bit of a riddle of trying to understand. You see here now it's been raining, and you see a lot of the higher level clouds. And you could see in the 1890s why by watching clouds you get a good view of how the winds are moving at different levels. If you know how high the cloud is and what type of cloud, you could learn a lot about that. So I don't know if I fully answered your questions, but this is sort of how we're trying to think about these problems, is how the humidity in the environment is affected by the clouds and affects the clouds. And through that, try to figure out what would happen in a warmer atmosphere. One thing we do know is that when you make the atmosphere warmer, you evaporate more water from the surface. And so in a way, you kind of accelerate the hydrological cycle. And so the hydrological cycle is how much water you evaporate and how much you rain. And this hydrological cycle is what makes the clouds bubble up. It's like a stewing pot. And so one of the theories that we have is that as the clouds bubble up, they mix more vigorously with the environment. So paradoxically, even though you're evaporating more water, the clouds are mixing more efficiently, and you have less clouds. So this is a reason to think that clouds might go away a little bit with warming. I tend to think in a lot of the models which have the strongest amount of warming that this effect is probably a bit exaggerated. So,
Question.
yeah.
Question is about human attempts to create or dissipate clouds.
I think creating clouds is hard because to create clouds, a lot of people get confused because cloud droplets form on little particles called aerosol particles or cloud condensation nuclei. It makes it easier for a water drop to condense. But the fundamental thing that has to happen first is air has to become saturated. So you need enough moist air that cools enough. And then if you have the little particles which are everywhere, then you'll form cloud droplets. But the basic condition to form a cloud is to saturate the air. So it's hard to create a cloud without changing air motions or without saturating air, just out of nothing. Most of the cloud modification attempts are really to modify weather, the ones I know of. You might be thinking of something else, but the way I interpreted your question was more the weather modification, but maybe you meant cloud modification. So what people try to do is they try to make clouds, existing clouds, brighter or less bright. So this goes into this class of ideas that some people call solar radiation management, which sounds like an innocuous name. But another name for it, some people call it geoengineering, but it's the idea of managing the amount of sunlight the planet gets by modifying the property of clouds. If you know, I can't even figure out how these clouds work all on their own. You know, if I could figure out a way to modify them, that would be brilliant. So sometimes I think there's a bit of hubris that humanity has in terms of its ability to control its environment. So it's fun if people want to think about how clouds work in a way that they think that they could actually change the cloud. But even that cloud, I couldn't tell if it was going to rain or not rain, let alone tell you how I could make it go away or not go away. So I'm a bit skeptical that these are really, you know, sometimes I kind of think these ideas come up from people who play with their computer models too long, that they think they can kind of control cloudiness and do all of these things. But I know there are certain ideas that somehow you could manage this whole Earth system. But when I look outside, I'm like, oh my goodness, I'm not going to be able to manage this, and it's best to try to minimize the harm that we do. So I don't put too much stock in some of these ideas. Did that answer your question enough? Yeah.
More questions? Oh, well, you next.
Could you make a comment on the shorter wavelengths of light on the water and climate?
Well, I was mostly talking about two wavelengths. The sun, which is visible wavelengths, which 500 nanometers, say, and then in the infrared, it's the microwave. Or thermal infrared down to the microwave. So they would be microns, so factors of 10 or so between that wavelength and these wavelengths, 10 or 20. And I'm not sure if you meant that there's yet shorter wavelengths, shorter than the visible, which we call ultraviolet, right? So the very short wavelengths are the ultraviolet. And then, so were you wondering about the ultraviolet or?
More the visible. Emphasizing more the infrared.
Okay. So the visible, it turns out that water vapor, for the most part, is transparent to visible light, but it's not perfectly true. Some of the modes of water vapor, the water vapor molecule is like that ballet dancer with the, I can't do her move, so I'll use my arms, with these two hydrogen atoms, and they, because of their vibrational modes, they absorb and give off infrared radiation, and there's some harmonics of these which go into the near infrared and near to the visible. So when you have lots of water vapor in the atmosphere, it begins absorbing sunlight. So increasing the amount of water vapor in the atmosphere begins to actually let the atmosphere absorb more energy in the short wavelengths. I don't know if, so water vapor actually interacts with visible light as well, and it gets more interesting the more you have. So if we make our planet really hot, so we all kind of go away, and we have a Venus, it will be kind of neat in the sense that we will have a lot of interaction between solar radiation, and if people were around to study it, it might even be more fascinating.
We have time for 2 more questions.
I just wondered, we know that the atmospheric oxygen was contributed in large part by respiration of bacterial organisms. And we know that there's an exchange of bacterial organisms with the atmosphere and with the oceans. Just wondered, is there any significant use of CO2 by bacterial organisms converting CO2 to oxygen that would be significant in any way as projected into the future?
Question is whether there's any use for microbes to convert CO2 to oxygen.
Now you're kind of going beyond my expertise a fair way, but I do think, one very exciting area scientifically is trying to understand ways of dealing with the extra CO2 that we have in the atmosphere. So I know within my scientific society, the Max Planck Society, there are groups of people who are trying to think of mechanisms or creating chemical or biological environments which are very effective at removing CO2 from the atmosphere. And if we could do this, this would be, right now it's just very expensive to remove CO2 from the atmosphere. But if there was a biological or chemical solution to that, that would be a tremendous breakthrough. So you guys here, Revere, get working on it. Save the world. I don't know if I don't know a lot about that area, so I hope that was kind of going in the direction. Yeah.
One more question.
What are some of the factors leading into a cycle of drought?
What are some of the factors leading into a cycle of drought?
The short answer is understanding things like periods of drought and heavy periods of rain, and looking at what controls regional scale weather patterns is an enormously challenging area of science, because there's a fair amount, and this is connected to Ed Lorenz, which is sort of fitting, because he was, when you think of the sort of aspects of our climate system which are related to things that aren't predictable, he really, one of the things I found fascinating was he was able to tell us some things that we can't tell you. We can't tell you what the weather is going to be with great precision in 15 days. We might be able to say more about large-scale droughts that are connected. If you look at this image here, if you look at this movie, there's large-scale circulation patterns here in this movie where you see very dry areas in the subtropics on average, like this here, but it won't always be dry. And so the subtropics is where we have the desert. So we can begin to say things about how you might see expansions of dry zones because we understand controls on the large-scale circulation. But if you look away from these areas where you might have regions which are intermediate, where sometimes you have wet and you have dry periods, that gets to be a lot harder subject. Of course, we'd love to know for lots of regions of economy and commerce and just human habitability, if regions are more susceptible to drought. There's a general feeling that as the planet warms, the dry areas will expand. So Carrie Emanuel's done some wonderful work on looking at how convection aggregates into smaller patches as the planet warms. And there's a lot of us who are trying to follow up some of these ideas to also see if that happens on yet larger scales. So the dry areas expand and the small and the wet areas contract. But these are really on the frontiers of the science. You can make lots of models, which we do, and run them forward in time, and you can get lots of numbers out of models. But I tend not to take things that come out of models too seriously until I can understand them myself. And these are things that I don't understand so well.
So unfortunately, our time has come to an end. we'd like to thank the New England Aquarium for making this stunning venue possible, in which we can not only see Bjorn's videos, but listen to him speak. And finally, let's thank Bjorn once again. Thank you.